Hello everyone, my name is Rupak Bose and I am from Indian Institute of Technology, Bombay. And I would like to thank GCPR for letting us present this paper. So I'll be presenting the paper Zero Shot Remote Sensing Image Super Resolution based on image continuity and self-tessellations, along with my co-authors Vikrant Rangnekar, Professor Biplab Banerjee and Professor Subhasis Chaudhuri. So the presentation has been structured in this way. Initially, we'll be introducing the problem statement, the challenges faced, and why this problem statement is important. Then we'll be moving forward with the architecture and the various modules that have been described in the architecture. Then we'll be discussing the results and the datasets which we have used for the evaluation of the results. Finally, we'll be concluding the presentation and we'll be opening up for the discussion. So, in a way, the term zero shot super resolution has been taken up because we have to super resolve images that the model has never seen before. Hence, what we have to do is the types of images which we will be training on will be discontinued or a disjoint set with the training images and the testing images. So those images we will be taking up will be coming from a mutually exclusive set. So the challenges would be the satellite images, they have diverse textures from fine grain to coarse grain textures. In cases of super resolution of urban areas, we can see that the slums have a very fine texture, whereas the building blocks, they have a very coarse texture. Also, the different classes can convey different information based on scale. For example, we need a very fine scale for urban area, whereas the super resolution of C won't be taking much effort because it is a very flat type of terrain. For example, another challenge would be high frequency components in the urban area versus the soft textures in the grasslands. So if a model is being trained on the high frequency components of the urban area, it will be definitely adding up noise while super resolving it, which can be detrimental in cases of soft textures that is found in the grasslands. The super resolution of grasslands when trained on urban area might introduce some artifacts based on noise. So what we have done is we have introduced a two-stream architecture, namely the content stream and the tessellation stream. Basically, this two-stream architecture takes input as these two photos, and then it performs a series of attention sharing on bottlenecks, and we cascade this as a cascaded autoencoder to finally get the high resolution tessellated image. So here the images we get are super resolved, and the attentions being shared between the content features and the tessellation features. This is the tessellation stream. So in tessellation stream, we input the tessellation feature images. So the tessellations, basically the tessellation, what we can term it as a repetitive pattern that can be generated, and this repetitive pattern needs to have satisfied some properties. So the basic property would be when we tessellate this image, the resulting image should also be image. So hence the image continuity property comes up. And the second property that we will be leveraging is the tessellated image should have a content or should give us a context that is corresponding to the original image. So this case is favorable in cases of remote sensing images, where we can see that tessellation of a remote sensing image, let us say of the class river, would definitely be a image of class river. So here we propose two tessellations. One is internal tessellation and the other is external tessellation. So in internal tessellation, we take a random patch and then we tessellate it out to get a bigger image, which will be a super resolved image. And then we use bilinear downsampling method to get a low resolution image. So we can sample randomly many areas to generate these data sets. The external tessellation would be we tessellate the actual input image many times to get a larger image, and then we can sample SR image and downsample it using bilinear downsampling. So that would be called as an external tessellation image. So another thing would be the content stream. Here, content stream is given. So the content stream basically takes up is the actual input image, and as you will see further, we use a autoencoder based format. So here, what we try to do is, even though the smaller local patterns are being learned by the tessellated stream, the global patterns will be learned by the content stream, and the attention features will be shared in both the streams so that the model learns local as well as global features, which are important for the super resolution task. So this is our proposed attention sharing mechanism. So what we have here is the content stream. The content stream goes along as the in an autoencoder format with skip connections between the left side of the bottleneck and right side of the bottleneck. Similar way, the tessellation stream is a bit deep autoencoded features where we'll be upsampling the features that we are getting, and the attentions are being shared between the bottleneck and the tessellation streamed outputs. So the attention sharing mechanism we can see here is what we do is we take the content features and apply a soft attention content features. Similar way, we take the tessellated features and we apply a soft attention on tessellated features. These attentions are then multiplied, cross multiplied with the other modality, and then we use the residual skip connection so that the features that are highlighted in the tessellated features can be highlighted similar way in the content features and vice versa. So on talking about soft attention, the soft attention is applied in the following way. What we do is we take the max pooling of the features that are generated and the mean pooling of the features. We do concatenate it, pass it through a multi-layer perceptron with the sigmoid activation. So here the sigmoid activation pushes all the weights between 0 and 1. And based on the importance of that feature, that layer's output would be closer to 1, whereas the other outputs would be less than 1. What we get from the soft attention layer is each of the layers are given a weightage as compared to the hard attention, where only the important layer will be given a weight and rest others are put forward to 0. So as you can see, we have demonstrated our results in the form of the remote sensing datasets of EuroSAT dataset, UCMerge dataset, and the PatternNet dataset. What you can see is we have compared our model with deep internal learning and meta zero shot super resolution model, and we have compared it with our model. As you can see that our model's outputs, they have more sharper features, as you can see here, as well as a better color accuracy. So in case of EuroSAT dataset, these are the images that you can see. In case of UCMerge dataset, when we zoom into the different models, we can see that here also our model significantly outperforms the other models. Here you can see the sharpness as well as the color reproducibility is way better than other models. As you can see here, this is the PatternNet dataset. In PatternNet dataset, as we can see, this is the class called as C/beach, which needs a bit of, let's say, color reproducibility. So in terms of color reproducibility, we can see that our model over here, our model has given us a significant improvement in the color, whereas some of the other models lack in display of colors. So here we have tabulated our results in the form of peak signal to noise ratio, structural similarity index measurement, and cosine similarity. The peak signal to noise ratio would be determining what is the peak signal of our image as compared to the mean squared error between the original image and our image. The structural similarity index measurement would show how structurally similar the generated image is with the ground truth, and cosine similarity would be checking the angular distance between the images. As this is a high dimensional output, cosine similarity shows us how near the output is irrespective of the dimension of the image. So what we can see here is, in case of UC merge dataset, our model performs well in case of PSNR, whereas the meta zero shot super resolution works better in cases of structural similarity. But our model isn't far behind meta ZSR. In case of cosine similarity, our model significantly outperforms the rest of the model. For the EuroSAT dataset, our model outperforms all of the other models that are available. In case of PatternNet dataset, even there we can see that our model significantly outperforms. So here what we have done is we have performed 2x scaling for super resolution. And for 2x scaling, what we wanted to see is the sharing of attention scores important, or is it playing a key role? So what we can see is these are the results with attention sharing mechanism activated. As you can see here, we have performed it for UC merge dataset, and the PSNR and other evaluation metrics significantly fall down because of not sharing our attention scores. Also, we have done an ablation study for the number of stacks in our model. And based on this, we can see that there does exist an optimum number of stack that can be used for super resolution. In conclusions, we would like to conclude by saying that the novelty that has been introduced by our model, that is attention sharing in the latent space, does work because the attention sharing mechanism ensures that the model is learning the global as well as the local features. Also, we have introduced a two-stream architecture for that, so that local as well as global features can be learned. So being it as a modular format, we can see that it can be easily stacked up and generated a deeper model. Also, we can say that use of internal statistics would definitely be instrumental in harnessing the image properties that can be used for better super resolution of the images. For future scope and discussions, we can see that there is a huge scope where we can introduce multiple modalities for attention sharing. For example, we can introduce hyperspectral images for better color reproduction, as well as we can introduce panchromatic images for better and sharper images. Also, the goal we can try to achieve is we can improve and enhance conventional telescopic images without the need of hardware upgradation. So this would ensure that we get to improve the image quality even though we are not being physically present to improve the hardware. Thank you.